There's something hauntingly beautiful about the idea that our universe is threaded together by forces we can't even see, forces so powerful. They sculpt galaxies like invisible hands molding clay. Picture this, a vast cosmic dance where stars whirl and spiral not just by gravity's pull, but by the silent, relentless tug of magnetism. This isn't science fiction. It's real, and yet, despite its colossal influence, cosmic magnetism remains one of the most enigmatic puzzles in all of space science. Think about that for a moment. We've mapped distant planets, peered into black holes, and traced the echoes of the Big Bang, but the magnetic fields weaving through the cosmos, they're still hiding their deepest secrets from us. Now, imagine standing at the edge of one of these uncharted territories, where the rules we thought we knew start to unravel. Places where magnetic fields twist into impossible shapes, where entire galaxies seem to defy logic, and where the very fabric of space hums with energy we don't yet understand. These aren't just abstract ideas, they're real, tangible mysteries waiting to be solved. And that's exactly where we're headed today. We're diving into 32 of these bewildering frontiers, each one a testament to how much we still have to learn about the universe. From magnetic monsters lurking in the voids between galaxies to the hidden forces that may have sparked the birth of stars, this journey will take us to the edges of our knowledge and beyond. What makes this exploration so thrilling isn't just the scale of these phenomena, though that alone is mind-bending. It's the humbling realization that every answer we uncover leads to even bigger questions. Cosmic magnetism doesn't just shape galaxies, it challenges our very understanding of physics, of space, even of time. And here's the thing, you don't need a telescope to feel the wonder of this mystery. It's written into the night sky, into the swirl of distant nebulae, into the silent pull that guides celestial bodies across the universe. So let's begin. Because somewhere out there, in the dark and the light, the cosmos is whispering its secrets, and we're finally learning how to listen. To grasp the invisible forces shaping our universe, we first need to understand how cosmic magnetism works at its core. Picture a river of charged particles, electrons and protons flowing through space. As these particles move, they create electric currents, and just like the current running through a wire here on Earth, those currents generate magnetic fields. But here's where things get cosmic. Instead of being confined to small circuits or planetary cores, these fields stretch across unimaginable distances, threading through galaxies and even the vast, seemingly empty voids between them. Now think of Earth's magnetic field as a simple bar magnet with clean lines running from pole to pole. Cosmic magnetism, on the other hand, is more like a tangled spiderweb, twisted and stretched by the violent motions of plasma, the births and deaths of stars, and the gravitational whirlpools around black holes. These fields don't just sit there, they are alive, shifting, sometimes snapping like rubber bands and releasing bursts of energy that can accelerate particles to nearly the speed of light. But why does this matter? Because without cosmic magnetism, the universe as we know it wouldn't exist. Take star formation, for example. When a cloud of gas collapses to form a new star, magnetic fields act like cosmic scaffolding, guiding and sometimes resisting the flow of material. Without them, stars might form chaotically or not at all. Then there's the way these fields shape entire galaxies, channeling cosmic rays, high-energy particles that zip through space, and even influencing how galaxies spin and evolve over billions of years. Yet for all we've learned, cosmic magnetism still holds countless mysteries. We don't fully understand how these fields first arose in the early universe, or why they appear stronger in some regions than others. Some galaxies seem to defy expectations, with magnetic fields that shouldn't exist based on our current models. And then there's the mind-bending possibility that magnetism might even play a role in the structure of space itself, weaving into the fabric of space-time in ways we're only beginning to imagine. So as we venture into the unknown, keep this foundation in mind. Cosmic magnetism isn't just some abstract force, it's a dynamic, shaping presence in the universe, as fundamental as gravity, yet infinitely more elusive. And that's what makes exploring its uncharted territories so exhilarating, because every time we think we've got it figured out, the cosmos throws us another curveball, reminding us just how much we still have to learn. One of the greatest cosmic detective stories begins with a question so fundamental it shakes our understanding of the universe. Where do these immense magnetic fields come from? We're not talking about the familiar pull of a refrigerator magnet. These are forces woven into the fabric of space itself, stretching across billions of light years. And their origin, that's where the mystery deepens. Some scientists argue these fields were born in the chaos of the early universe, when space was a seething ocean of plasma, hotter and denser than anything we can recreate. In those first moments, tiny quantum fluctuations could have sparked magnetic seeds, amplified over eons by the motion of charged particles, like whispers growing into shouts across cosmic time. This idea, called primordial magnetism, suggests these fields might be as ancient as the Big Bang itself, woven into the universe's very blueprint, but others propose a different story. Imagine the first stars flickering to life in the cosmic dark, their violent death spewing charged particles into the void, or supermassive black holes, their jets acting like cosmic particle accelerators, twisting space with magnetic energy. In this view, magnetism didn't start with the universe, it emerged later, sculpted by the very structures it now shapes. Here's where it gets fascinating. Recent observations of galaxies born just a few 100 million years after the Big Bang show something astonishing. They already have strong, organized magnetic fields. That's like finding a fully formed city in what should be a barren wilderness. If magnetism took time to grow, how did these young galaxies get their fields so quickly? The timelines don't add up, and that's forcing scientists to rethink everything. What if magnetism isn't just a side effect of the universe's evolution, but something more fundamental? Gravity shapes the cosmos on the largest scales, but magnetism might operate on a level we're only beginning to grasp. Some theories even suggest these fields could be tied to dark matter or dark energy, those other great cosmic mysteries. If true, solving this puzzle wouldn't just explain magnetism, it could unlock secrets about the universe's hidden architecture. So while we don't have all the answers yet, one thing's certain: every new discovery peels back another layer of this enigma. Whether magnetism was there at the dawn of time or emerged from the cosmic drama that followed, its story is far from written. And that's what makes this first uncharted territory so exhilarating, because somewhere in this mystery lies a clue that could change how we see the universe forever. If the cosmos has taught us anything, it's that emptiness is an illusion. Take the vast voids between galaxies, regions so sparse, they were long considered cosmic deserts, stripped of structure and silent in the grand magnetic symphony of the universe. But the universe loves a good surprise. Recent observations have revealed something astonishing. Even here, in these seemingly barren expanses, faint magnetic fields hum quietly, threading through the void like ghostly whispers. How is this possible? In places where matter is almost non-existent, where the density is 1,000,000 times lower than in galaxies, what could possibly sustain these elusive fields? One compelling theory points to the echoes of ancient violence. Picture a galaxy in its youth, ferocious and tempestuous, spewing colossal winds of charged particles as stars are born and die in rapid succession. These galactic hurricanes could have flooded the voids with magnetic energy billions of years ago, imprinting fields that never fully faded. Like footprints fossilized in cosmic mud, these remnants might still linger, faint but detectable, a testament to the universe's turbulent past. But there's another, even more intriguing possibility. What if magnetism isn't just a relic here? What if it's actively maintained? Some researchers suggest that the voids aren't truly empty, but laced with tenuous filaments of gas, a cosmic web too faint to see directly. Within these threads, weak electric currents might still flow, driven by the subtle motions of the sparse particles present. Over eons, these currents could regenerate magnetic fields, turning the void into a slow-motion dynamo, quietly sustaining itself against all odds. Then there's the truly mind-bending idea that these fields aren't tied to matter at all. Could magnetism be a fundamental property of space itself, woven into the vacuum like an invisible tapestry? It's a radical thought, but if true, it would mean the void's magnetism isn't just leftovers, it's part of the universe's deeper architecture, as inherent as space-time. Whatever the answer, one thing is clear: these ghostly fields are rewriting the rules. They hint at a universe far more interconnected than we imagined, where even the emptiest spaces hum with hidden forces. And that raises another tantalizing question. If magnetism stretches unbroken through the void, could it be guiding the formation of galaxies, shaping the cosmos not just from within, but from the outside in? The void, it seems, is anything but empty. It's a frontier alive with mystery, and we're only beginning to glimpse its secrets. Galaxies aren't just islands of stars, they're colossal magnetic engines humming with invisible energy. Take our own Milky Way. Its spiral arms aren't just glowing with starlight, they're threaded with magnetic fields so vast they stretch from one end of the galaxy to the other. But here's the puzzle: how do these fields stay so strong, so organized for billions of years? Enter the galactic dynamo, one of the universe's most fascinating tricks for turning chaos into order. Picture a river of ionized gas, superheated and electrified, swirling through a galaxy's disk like water spiraling down a drain. As this charged plasma moves, it drags magnetic field lines with it, twisting and stretching them like taffy. But here's where the magic happens. Those motions don't just distort the fields, they amplify them. Weak, scattered magnetic energy gets tangled up in the galaxy's rotation, and over time, that turbulence actually strengthens the field like a cosmic feedback loop. It's as if the galaxy is generating its own magnetism, a self-sustaining cycle that defies entropy. Yet for all its elegance, the dynamo theory leaves gaps wide enough to fly a starship through. Computer simulations, even the most advanced ones, can't quite replicate the intricate magnetic patterns we observe in real galaxies. Some regions show fields that flip direction abruptly, like cosmic switchbacks, while others are turbulent maelstroms where magnetism seems to rebel against all order. And then there's the sheer endurance of these fields. How do they persist, virtually unchanging, across timescales longer than Earth's entire existence? Part of the answer might lie in the hidden architecture of galaxies themselves. Think of a spiral galaxy not just as a flat disk, but as a dynamic, three-dimensional structure. Galactic fountains, torrents of gas blasted upward by supernova, could be threading magnetic energy from the disk into the halo above, creating feedback loops that stabilize the field. Meanwhile, the chaotic churn of star-forming regions might act like cosmic mixers, stirring the magnetic brew in ways we're only beginning to map, but the real enigma. Some galaxies defy the dynamo entirely. A handful of distant spirals show magnetic fields too strong, too coherent to be explained by known physics. It's as if we're missing a piece of the puzzle, something beyond swirling gas, beyond even black holes. Could there be an exotic energy source at work, or a deeper connection between magnetism and dark matter? Every observation seems to raise new questions, proving that the galactic dynamo isn't just a mechanism, it's a living mystery, one that might hold the key to understanding how galaxies are born, evolve, and ultimately, how they shape the universe around them. So while we've unraveled part of the dynamo's secret, the full story remains written in the stars and in the invisible forces weaving between them. What we do know is this: magnetism isn't just a side effect of galactic life. It's a driving force as essential as gravity and far more enigmatic. And that's what makes this uncharted territory so thrilling, because somewhere in the whirl of ionized gas and the snap of magnetic fields lies a revelation that could rewrite our cosmic playbook. Dark matter and magnetism, two of the cosmos' greatest mysteries, might be far more intertwined than we ever imagined. For decades, dark matter has been the universe's silent architect, its gravitational pull sculpting galaxies into being while remaining utterly invisible to our telescopes. But what if this elusive substance doesn't just lurk in the shadows? What if it leaves fingerprints on the magnetic fields weaving through space? This tantalizing possibility could rewrite our understanding of both dark matter and the forces shaping the cosmos. Consider how dark matter behaves. We know it clumps around galaxies in vast halos, exerting gravitational influence without emitting light. But magnetism thrives on motion-charged particles moving through space, generating currents. If dark matter particles carried even a faint electromagnetic charge, their movements could subtly alter the magnetic fields around them. Picture a river flowing past a hidden boulder. The water bends, revealing the obstacle beneath. Similarly, distortions in galactic magnetic fields might betray dark matter's presence, offering us a way to see the unseeable. Then there's the flip side: magnetism's potential influence on dark matter. Most models assume dark matter interacts only through gravity, drifting like fog through the universe. But if magnetic fields could nudge these particles even slightly, the implications would be staggering. Galactic magnetic fields might act like cosmic shepherds, guiding dark matter into denser clumps or stretching it into filaments along invisible lines of force. Suddenly, the distribution of dark matter, the very scaffolding of the cosmos, wouldn't just be gravity's handiwork. It would be a collaboration between two fundamental forces, one seen and one unseen. Some of the most compelling hints come from the anomalies we can't explain. Take certain dwarf galaxies, where dark matter appears to cluster more densely than theories predict. Could localized magnetic fields be funneling dark matter into these tight knots? Or consider the bizarre dark flow, a mysterious cosmic current where entire galaxy clusters drift in unison, as if pulled by something beyond the observable universe. If dark matter and magnetism are entangled, could their combined forces be driving this motion? Of course, not all scientists are convinced. Skeptics argue that dark matter's ghostly nature makes electromagnetic interaction unlikely. But the beauty of science lies in its surprises. Just last year, researchers detected faint, unexpected twists in the magnetic fields surrounding distant galaxy clusters, twists that align suspiciously with dark matter maps. It's as if the universe is dropping breadcrumbs, urging us to follow. Whether this connection proves real or not, one thing is certain: exploring it pushes the boundaries of physics. Confirming that dark matter interacts with magnetism would open a new window into the invisible 95% of the universe we don't understand. It would mean that magnetism isn't just a player in the cosmic drama, it's a bridge between the seen and the unseen, a force whispering secrets about the deepest mysteries of existence. And that's why this uncharted territory isn't just fascinating, it's revolutionary. Imagine holding a magnet in your hand, break it in half, and you don't get isolated north or south poles. Instead, you're left with two smaller magnets, each still sporting both poles. This duality is so fundamental to magnetism that for centuries, scientists assumed it was an unbreakable law of nature. But what if we've been wrong? What if somewhere in the universe, particles exist with just a single magnetic charge, a pure north or pure south, untethered from their opposite? Welcome to the mind-bending hunt for magnetic monopoles, one of physics' greatest what-ifs. The idea isn't just wild speculation. Some of the most ambitious theories of the cosmos, like grand unified theories linking all fundamental forces, demand that monopoles should exist. In the searing heat of the early universe, fractions of a second after the Big Bang, conditions might have been just right for these exotic particles to form. Think of them as cosmic relics, frozen into existence when the universe was 1 trillion times hotter than the core of the Sun. If even a handful survived, they'd be drifting through space today, ghostly fingerprints of a time before time. So why haven't we found them? Part of the challenge is their elusiveness. Monopoles wouldn't behave like ordinary matter. A single one could carry a magnetic charge stronger than an entire planet's field, yet be smaller than an atom. They might streak through Earth like cosmic bullets, leaving barely a trace. Some experiments have hunted for them in ancient minerals, where monopoles could have left scars as they passed through. Others have scanned the depths of space, hoping to catch one embedded in cosmic rays. So far, silence, but here's where it gets even stranger. If monopoles vanished after the Big Bang, their absence might explain another mystery: why the universe's magnetic fields are so weak. Theory suggests the early cosmos should have been flooded with monopoles, their interactions sapping magnetic energy. Their disappearance could be the reason magnetism today is a whisper rather than a shout. Alternatively, what if they're still out there, hiding in plain sight? Some physicists speculate that monopoles could have clustered in the cores of neutron stars or even shaped the distribution of galaxies, their gravity subtly warping the cosmos. The stakes couldn't be higher. Finding a monopole wouldn't just rewrite physics textbooks, it would prove that forces we thought were inseparable can be torn apart, revealing a deeper layer of reality. It would mean our universe is far stranger, far more malleable than we ever imagined, and that's the thrill of this uncharted territory. Whether monopoles are waiting to be discovered or forever lost to time, their mystery forces us to ask, what else have we missed? What other invisible threads are woven into the fabric of space just beyond our grasp? The search continues because in the hunt for monopoles, we're not just chasing a particle, we're chasing the possibility that the universe still has secrets bold enough to surprise us. We think we know our galactic home, but the Milky Way has a way of humbling even the most confident astronomers. Look up at the night sky, and you're not just seeing stars, you're gazing into a labyrinth of magnetic mysteries, where invisible forces twist and turn in ways that defy logic. Take those eerie filaments near the galactic center, for example. These bizarre structures stretch hundreds of light years like cosmic spider silk, crackling with magnetic energy. They shouldn't exist, not here, not like this. Conventional physics says magnetic fields should diffuse or tangle over such distances, yet these filaments remain stubbornly coherent, as if some unseen hand is combing them into perfect alignment. Some theorists whisper about black hole winds or shockwaves from ancient stellar explosions, but no one knows for sure. Then there's the Milky Way's magnetic patchwork. Most galaxies show some variation, but ours is a study in extremes. In places like the Scutum Centaurus arm, the field is a roaring tempest, strong enough to steer entire clouds of star-forming gas. Yet just a few thousand light-years away, in regions like the Orion Spur, the magnetism fades to a whisper, as if someone flipped a cosmic off switch. What could cause such wild disparities? One clue might lie in our galaxy's violent past. Collisions with dwarf galaxies, bursts of star formation, even the reverberations of long-dead supernova could have sculpted these magnetic deserts and jungles over billions of years. But here's the twist: some of these regions appear too young to fit that story. Their magnetic signatures are fresh, almost impulsive, as if something is actively shaping them right now. And then there are the stars, especially the oddballs like HD 45166, a star with a magnetic field so powerful it defies every model of stellar physics. It's as if someone took a neutron star's magnetic fury and crammed it into a sun-like body. Normally, stars this old should have settled into magnetic middle age, their fields fading like embers. Instead, they're burning brighter, stranger. Could these anomalies be remnants of ancient mergers where two stars collided and merged their magnetic histories? Or is there some unknown mechanism, a hidden dynamo deep in stellar cores, that we've yet to uncover? The deeper we look, the clearer it becomes. The Milky Way isn't just a collection of stars. It's a living magnetic laboratory where the rules we've written seem to bend and warp. Maybe the answer lies in dark matter's invisible grip, or in relics from the galaxy's birth frozen in time. Or perhaps, just perhaps, we're seeing hints of a deeper truth, that magnetism isn't just a side effect of cosmic evolution, but a fundamental language the universe uses to sculpt itself. Whatever the case, one thing's certain: our galactic backyard holds secrets wilder than we've dared to imagine, and they're waiting just out of sight for us to piece them together. Black holes and neutron stars don't just devour matter, they spit it back out with unimaginable fury. Picture this: jets of superheated plasma, stretching tens of thousands of light years into the void, moving so fast they'd cross the entire solar system in the blink of an eye. These aren't just cosmic fireworks, they're some of the most powerful particle accelerators in the universe, and their secret weapon, magnetism. But here's the puzzle: how do these invisible fields take ordinary particles and fling them to near light speed with such precision? The answer might lie in a cosmic tug of war between gravity and magnetism. Near a black hole or neutron star, the gravitational pull is so intense that infalling gas spirals into a swirling disk, hotter than the core of a star. As this plasma churns, it drags magnetic field lines with it, twisting them into knots of unimaginable tension. Think of it like winding up a rubber band until it snaps, except here, when the fields finally break, they don't just release a flick of energy. They catapult charged particles outward in jets so focused they could pierce through galaxies. But the details, that's where things get messy. Some models suggest these jets are powered by magnetic reconnection, a process where field lines break and reconnect, launching bursts of energy like a cosmic slingshot. Others argue it's the sheer spin of the black hole itself, acting like a dynamo and turning space-time itself into a particle accelerator. Then there's the wild card: plasma instabilities we don't fully understand, where turbulence in the disk might amplify magnetic fields to levels that defy our best simulations. What's truly baffling is how these jets stay so tightly collimated over such vast distances. On Earth, any beam of energy would spread out and dissipate, but these cosmic jets remain razor-sharp for millennia. Some researchers think magnetic fields act like invisible pipelines, keeping the particles locked in a focused stream. Others speculate there's a feedback loop at play, where the jets themselves reinforce the fields that guide them, a self-sustaining cycle of acceleration. And the implications, they're staggering. If we could decode the physics behind these jets, we might unlock new ways to generate energy, not just in space, but here on Earth. Imagine harnessing even a fraction of that magnetic efficiency, clean, limitless power drawn from the same forces that shape galaxies. But beyond practicality, solving this mystery would rewrite our understanding of how energy moves through the cosmos. These jets aren't just celestial curiosities, they're proof that magnetism, when pushed to extremes, can bend the very rules of physics. So while we're still piecing together how these cosmic accelerators work, one thing's clear: black holes and neutron stars are more than just gravitational monsters. They're master sculptors of magnetic energy, wielding forces so potent they can launch matter across the universe. And somewhere in that chaos, hidden in the twist of magnetic fields and the scream of plasma, lies a secret waiting to transform how we see the cosmos. There's a hidden cosmic fireworks show happening all around us, one so powerful it can outshine entire galaxies. But you won't see it with the naked eye, because the real spectacle happens when invisible magnetic field lines snap like overstretched rubber bands, unleashing enough energy to vaporize planets. This is magnetic reconnection, one of the universe's most explosive secrets. Picture two rivers flowing in opposite directions, their currents colliding with enough force to fling water high into the air. Now replace those rivers with magnetic fields in plasma superheated, electrified gas, and you've got the recipe for cosmic chaos. When these field lines break and violently reconnect, they don't just release a spark. They detonate with the force of billions of atomic bombs, accelerating particles to nearly the speed of light. We've seen it happen close to home, in solar flares that disrupt satellites and paint the sky with auroras. But out in deep space, reconnection events reach unimaginable scales, powering eruptions that make our sun's tantrums look like candle flames. What baffles scientists isn't just the scale, it's the speed. In labs, reconnection crawls along at a snail's pace, but in space, it happens faster than theory predicts, like a zipper suddenly yanked open by invisible hands. Some think turbulence in the plasma acts like cosmic lighter fluid, igniting explosions in milliseconds. Others point to strange quantum effects that might let particles cheat physics, tunneling through magnetic barriers to trigger chain reactions. Then there's the wild card. Could dark matter or exotic particles be playing referee in these collisions, tweaking the rules when we're not looking? The stakes go beyond curiosity. Gamma-ray bursts, the most violent explosions since the Big Bang, might owe their fury to reconnection events near newborn black holes. Quasars, those brilliant beacons from the early universe, could be powered by magnetic snapshots in their accretion disks. Even the jets screaming from galaxy cores might rely on reconnection to stay focused across millions of light years. Yet for all its destructive power, reconnection might also be a cosmic architect. Some theories suggest it could seed star formation by shocking cold gas clouds into collapse. Others speculate it helped shape the large-scale structure of the universe, carving channels through which galaxies eventually flowed. It's a reminder that in space, creation and destruction are two sides of the same coin, and magnetism holds the flipping hand. So while we're still piecing together why reconnection defies our expectations, one thing's certain: these invisible explosions are rewriting the story of how energy moves through the cosmos. They're proof that even in the emptiest voids, hidden forces are at work, twisting, snapping, and remaking the universe one magnetic line at a time. We float through space inside a cosmic oddity, a vast, cavernous region known as the local bubble, stretching over 300 light-years wide. It's not empty, but filled with thin, scorching gas, the remnants of ancient stellar explosions that cleared out this pocket of the galaxy millions of years ago. Yet there's something stranger here than just the ghostly afterglow of supernova. Recent observations reveal our solar system isn't just drifting through this bubble, it's encased in a magnetic cocoon, a shell of invisible force lines wrapping around the cavity like an invisible fence. And no one knows exactly how it got there. One theory points to the violent births of those long-dead stars. When massive stars explode, they don't just blast material outward. They flood space with magnetized debris, a turbulent soup of charged particles and twisted field lines. Over millennia, these fields could have been stretched and folded by the bubble's expansion, like taffy pulled thin until it formed this eerie magnetic boundary. If true, the shell around us isn't just a relic, it's a fossil, preserving the fury of stellar deaths from an era before Earth even existed. But there's a competing idea, one that ties our bubble to the galaxy's grander design. The Milky Way isn't a blank canvas, it's threaded with vast, overarching magnetic fields, shaped by the slow churn of interstellar gas and the rotation of the galaxy itself. Some researchers argue the local bubble's shell might not be a leftover at all. Instead, it could be the result of our cavity pressing against this larger galactic field, compressing and amplifying it at the edges like a snowplow piling up drifts. In this scenario, the bubble isn't just a passive structure, it's actively reshaping the magnetism around it, creating a ripple in the galaxy's invisible fabric. Here's where it gets even weirder. Measurements show the shell's magnetic field isn't uniform, it's patchy, stronger in some spots and nearly absent in others. That inconsistency throws a wrench in both theories. If the shell were purely supernova debris, we'd expect a more chaotic but evenly distributed field. If it were purely galactic pressure, the structure should be smoother. So what's causing these irregularities? Some speculate that long-gone stellar winds or the gravitational tug of nearby star-forming regions might have warped the shell over time. Others wonder if dark matter's invisible hand could be subtly tweaking the field's geometry in ways we can't yet detect. The implications go far beyond curiosity. This magnetic shell isn't just a cosmic decoration, it's a filter, shaping how high-energy particles from deep space reach our solar system. Galactic cosmic rays, those high-speed atomic bullets hurtling through the void, might be deflected or focused by the bubble's field, altering the radiation environment around Earth. That means this enigma isn't just a distant mystery, it's a silent player in the story of life itself, influencing the very conditions that allowed our planet to thrive. So while we're still piecing together the local bubble's magnetic secrets, one thing is certain: our cosmic neighborhood is far more dynamic than we ever imagined. It's not just empty space out there, it's a living, shifting landscape of invisible forces, and we're only beginning to map its contours. And somewhere in that map, hidden in the twists and turns of magnetic lines, lies a clue that could rewrite how we see our place in the galaxy. Galaxies don't drift through the cosmos alone, they gather in clusters, bound together by gravity like islands in a vast ocean. But there's something else holding these cosmic metropolises together, something invisible yet astonishingly powerful: intergalactic magnetic fields. Picture this: threads of magnetism, not just spanning individual galaxies, but stretching across millions of light years, weaving through the superheated gas that fills the spaces between them. These fields aren't faint whispers, they're strong, organized, and eerily coherent, as if some cosmic loom carefully stitched them into place. How do these vast magnetic webs form? One leading theory suggests they started small, tiny seeds of magnetism born in the chaos of the early universe, perhaps from the turbulent wakes of the first galaxies. Over billions of years, as galaxy clusters grew, the motion of galaxies through this hot intergalactic gas could have stretched and amplified these weak fields, like taffy pulled thin until it formed a vast, invisible tapestry. Imagine a spoon stirring honey. The swirling motion creates ripples and strands, now scaled at up to galactic proportions, with entire galaxies acting as the spoons, churning the magnetized plasma between them into intricate patterns. But there's another, even more intriguing possibility: cosmic dynamos operating on scales we can barely comprehend. Just as galaxies generate their own magnetism through the motion of charged particles, these colossal clusters might harbor dynamos of their own, hidden in the turbulent flows of intergalactic gas. Supermassive black holes at the hearts of galaxies could be key players here, their jets pumping energy and magnetism into the surrounding void like cosmic fire hoses. Over time, these injections might build up into the organized fields we see today, fields so vast, they make entire galaxies look like specks in their grip. What's truly mind-bending is how these fields shape the universe around them. They're not passive bystanders. Intergalactic magnetism can steer the paths of high-energy cosmic rays, influence how galaxy clusters collide and merge, and even regulate the flow of gas that fuels star formation. Some researchers speculate these fields might act like cosmic highways, channeling matter and energy along invisible routes, shaping the large-scale structure of the universe itself. Yet for all we've pieced together, the puzzle is far from complete. Some galaxy clusters show magnetic fields that are too strong, too uniform to fit our current models. Others display bizarre twists and kinks, as if something or someone has tugged at the fabric of these invisible threads. Could dark matter be interacting with these fields in ways we don't yet grasp? Or are we seeing echoes of an even older mystery, something dating back to the universe's infancy? One thing's certain: these intergalactic magnetic fields are more than just cosmic decoration. They're a fundamental part of the universe's architecture, as essential as gravity in shaping the story of galaxies, clusters, and everything in between. And every new discovery peels back another layer, revealing just how much we still have to learn about the invisible forces binding the cosmos together. Neutron stars are nature's most extreme laboratories, cosmic pressure cookers where matter is squeezed so tightly, a single teaspoon would weigh 1 billion tons. But it's not just their density that defies imagination. These stellar corpses harbor magnetic fields so intense, they bend the very rules of physics. Take magnetars, the most magnetic monsters of all. Their fields reach strengths of 1,000 trillion times Earth's, so powerful they could strip the data off a credit card from halfway across the solar system. Yet for all their ferocity, these stars are full of contradictions. Some neutron stars, born from the same violent supernova, inexplicably have fields millions of times weaker. Others flicker between strong and weak states like a cosmic light switch. What's going on inside these enigmatic objects? The answer might rewrite our understanding of matter itself. At the heart of the mystery lies quantum soup, a neutron star's core, where gravity crushes atoms into a bizarre state called neutron superfluidity. Here, particles flow without friction, while protons form superconducting currents that could sustain magnetic fields for eons. But twist the conditions slightly and everything changes. Imagine a vat of swirling quantum fluid suddenly developing turbulent pockets where superconductivity breaks down. These glitches could cause magnetic fields to reconfigure, explaining why some neutron stars abruptly shift between strong and weak states. It's as if the star's interior is a colossal circuit board, with invisible switches flipping beneath the surface. Then there's the puzzle of magnetar eruptions, violent starquakes where the crust, under unimaginable strain from twisting magnetic fields, suddenly cracks. The energy released in these events can outshine the entire Milky Way for a fraction of a second, But here's the catch: not all magnetars erupt with the same fury. Some are relatively quiet, while others unleash apocalyptic bursts at irregular intervals. The difference might come down to geometry. If magnetic field lines inside the star become tangled like spaghetti in a bowl, stress builds unevenly. A slight rearrangement could trigger a modest quake or snap the fields entirely, unleashing a catastrophic flare. But the real head-scratcher is the neutron stars that shouldn't exist. Take the case of Gyro J1742, a star with a magnetic field too weak to power its intense X-ray emissions. Conventional models say it should be dark, yet it shines defiantly. Some theorists speculate these outliers might be hiding exotic states of matter-free quarks, hyperons, or even particles we haven't discovered yet, altering how magnetism propagates through their cores. Others suggest they're ancient magnetars in disguise, their once mighty fields having decayed over millennia into cryptic new configurations. The implications stretch far beyond stellar curiosities. If we can decode the secrets of neutron star magnetism, we might unlock new frontiers in energy storage, materials science, even quantum computing. These stars are testing grounds for physics under conditions we could never replicate on Earth. Every flicker, every eruption, every anomalous field is a clue, a whisper from the edge of what's possible, and that's what makes this uncharted territory so electrifying. Because when you peer into the heart of a neutron star, you're not just studying a celestial object, you're staring into a looking glass where the known laws of nature warp into something stranger, wilder, and more beautiful than we ever dreamed. Before a star flickers to life, its birthplace is a swirling, chaotic dance of gas and dust, a protostellar disk where the seeds of planets take shape. But hidden within this cosmic nursery, an invisible puppeteer pulls the strings: magnetic fields. These forces don't just linger passively, they twist and warp the disk, sculpting the very material that will one day become worlds. Yet the more we observe these disks, the more baffling their magnetic behavior becomes. Some show fields neatly aligned with the disk's rotation, like orderly spiral arms. Others reveal fields bent into chaos, as if some unseen hand crumpled them like paper. What's causing this wild inconsistency? And more importantly, how does it shape the fate of emerging planetary systems? One clue lies in the delicate balance between magnetism and motion. As a protostellar disk spins, charged particles within it generate electric currents, which in turn produce magnetic fields. In theory, these fields should act like cosmic traffic cops, guiding dust grains to clump together gently, eventually snowballing into planets. But reality is messier. In some disks, the fields grow so strong they overpower gravity, flinging material outward before it can coalesce. In others, turbulence tangles the fields into knots, creating pockets where planets form faster or slower than expected. It's as if each disk has its own magnetic fingerprint, dictating whether it will birth orderly solar systems like ours or chaotic ones with planets flung into erratic orbits. Then there's the mystery of misaligned fields. Take the young star Tauri, its disk a stunning bullseye of concentric rings where planets may be forming. Observations reveal its magnetic field isn't parallel to the disk at all, it's tilted, as if someone knocked it askew. Could this explain why some exoplanet systems orbit at bizarre angles compared to their stars? Some theorists suggest these warped fields arise from cosmic collisions nearby stars or passing gas clouds tugging at the disk's magnetism like a magnet dragged past a compass. Others propose the star itself is to blame, its newborn magnetic field battling with the disks in a celestial tug of war. But the biggest enigma is how these fields vanish. By the time planets finish forming, most protostellar disks have lost their strong magnetism, leaving behind systems governed by gravity alone. Does the field dissipate as the star awakens, its radiation blowing away the charged particles that sustained it, or does it get buried, trapped beneath the surface of newly minted worlds? Some researchers even speculate that remnants of these primordial fields might linger in planetary cores, fueling the magnetic shields that protect planets like Earth to this day. The stakes couldn't be higher. If we crack the code of protostellar magnetism, we might finally understand why our solar system looks the way it does, and why others defy expectations. Are orderly systems like ours the exception, sculpted by just the right magnetic conditions, or is chaos the norm, with Earth's tranquil neighborhood a cosmic fluke? Every disk we study is a time capsule, preserving the magnetic whispers of its birth. And somewhere in those whispers lies the answer to one of astronomy's oldest questions. How does a cloud of dust become a home for life? The cosmic web is the universe's grandest architecture, a sprawling network of galaxies, gas, and dark matter stretching billions of light years, connected by delicate filaments so vast they make entire superclusters look like mere knots in the tapestry. But what if this web isn't just held together by gravity? What if magnetism, silent and unseen, threads through these cosmic highways like an invisible current? Recent observations hint that magnetic fields might not just exist within the web, they might trace its very shape, as if the universe itself sketched these lines with a magnetic pen. Imagine standing at the edge of one of these filaments, where galaxies flow like beads on a string. Between them, the space isn't empty. It's thrumming with ionized gas, superheated and electrified, capable of carrying magnetic fields across unfathomable distances. Some theories suggest these fields could have been stretched along the filaments as the web formed, like taffy pulled thin during the universe's expansion. Others propose something even more radical, that magnetism played an active role in sculpting the web's structure from the beginning. Picture the early universe, a seething plasma where magnetic forces nudged matter into denser threads, guiding the birth of galaxies along magnetic fault lines. Yet the evidence is maddeningly elusive. Detecting these faint fields is like trying to hear a whisper in a hurricane. Some radio telescopes have caught hints of polarized light, twisted by magnetism as it travels through the web's filaments. In galaxy clusters where filaments intersect, the fields appear stronger, as if the cosmic web's crossroads amplify their signal. But the real shock came when researchers found similar magnetic alignments in completely unrelated regions of the web, too far apart for local forces to explain. It's as if the universe imprinted these fields with the same cosmic stamp, a pattern woven into space itself. This raises a dizzying possibility. Magnetism might not just be a passenger riding the cosmic web, it could be part of its foundation. If the fields were present in the universe's infancy, they might have steered the flow of matter, helping gravity sculpt the web's filaments into existence. Alternatively, the web's formation could have stretched and amplified primordial magnetic seeds, like a painter dragging a brush across canvas. Either way, the implications are staggering. Maps of the cosmos might need a new dimension, one that charts not just mass and light, but the invisible magnetic currents flowing through everything. And then there's the dark matter puzzle. If magnetism threads the web, could it interact with dark matter's elusive particles? Most models assume dark matter ignores electromagnetic forces, but what if there's a subtle interplay? Some filaments glow with unexplained radiation, as if their magnetic fields are tapping into an unseen energy source. Could dark matter be the battery? Or are we seeing something even stranger, a hidden layer of physics where magnetism bends the rules we thought were written in stone? Every new observation deepens the mystery. Some filaments show magnetic fields neatly aligned along their length, while others twist like corkscrews, defying expectations. In the voids between them, where matter is scarcest, faint magnetic whispers still linger, ghosts of a force that refuses to stay confined. It's as if the universe is teasing us, revealing just enough to upend our assumptions but never enough to solve the riddle. One thing's certain: if magnetism truly traces the cosmic web, it's not just a footnote in astrophysics, it's a fundamental language of the universe, as essential as gravity in shaping the story of everything. And deciphering that language could rewrite how we understand the cosmos, from the birth of galaxies to the fate of the universe itself. The web's magnetic threads aren't just hidden pathways, they're clues waiting to be pulled. The sun may seem like a steady cosmic heartbeat pulsing with an 11-year magnetic cycle as reliable as clockwork, but dig deeper, and you'll find it's full of surprises. Every decade or so, its magnetic poles flip like a metronome swinging the other way, driving sunspot activity, solar flares, and the auroras that paint our skies. But sometimes that rhythm stutters, fields weaken unexpectedly, reversals arrive late, or worse, barely happen at all. These anomalies aren't just curiosities, they're cosmic disruptions with real consequences for Earth, and their origins remain one of the sun's best-kept secrets. Take the Maunder minimum, a 70-year period starting in the 1600s when sunspots virtually vanished. During this great solar silence, Earth plunged into what we now call the Little Ice Age. Frost fairs on the Thames, glaciers swallowing villages, crops failing across Europe. Coincidence? Hardly. Studies show that when the sun's magnetic activity dips, Earth's climate responds, though the exact mechanism is still debated. Some argue weakened solar wind lets more cosmic rays bombard our atmosphere, seeding cloud formation. Others point to subtle shifts in the sun's ultraviolet output, altering stratospheric winds. Whatever the link, one thing's clear: the sun's magnetic mood swings are written into our planet's history. So what causes these anomalies? The leading suspect lurks beneath the sun's fiery surface, deep in its convection zone, where plasma churns like a boiling ocean. Magnetic fields are thought to regenerate in a process called the solar dynamo. But sometimes the dynamo sputters. Imagine a car engine misfiring, perhaps due to uneven rotation in the sun's interior, where the equator spins faster than the poles, stretching and twisting magnetic fields until they tangle. Or maybe magnetic ropes, bundles of field lines rising from the depths, get jammed before they can break the surface, delaying the polar flip. There's even evidence of a hidden second dynamo near the sun's core, operating on a longer cycle that might interfere with the main one like a dissonant chord in a symphony. But here's where it gets wilder. What if the sun's irregularities aren't entirely its own doing? Some researchers speculate that external forces, cosmic magnetism on a galactic scale, could be nudging our star's behavior. The solar system isn't stationary. It moves through the Milky Way, passing through regions with varying magnetic fields. Could these interstellar tides subtly influence the sun's dynamo, like the moon tugging on Earth's oceans? It's a radical idea, but recent data shows odd correlations between solar minima and our position relative to the galaxy's spiral arms. If true, it would mean the sun's cycles are part of a much larger cosmic conversation. The stakes are higher than academic curiosity. A delayed or weakened solar cycle isn't just a climate concern, it's a technological vulnerability. During periods of low solar activity, harmful cosmic radiation penetrates deeper into the solar system, threatening satellites and astronauts. Meanwhile, extreme space weather events like coronal mass ejections can still strike even during a quiet sun, catching us off guard. Understanding these anomalies could revolutionize space weather forecasting, giving us crucial extra hours to shield power grids, reroute flights, and protect critical infrastructure. Yet for all we've pieced together, the sun's magnetic mysteries resist easy answers. Like a patient withholding symptoms, it offers clues. A missed reversal here, a strangely weak field there, but keeps its deepest workings hidden beneath layers of plasma. Perhaps the key lies in upcoming missions like the European Space Agency's Vigil probe, designed to monitor the sun's poles for the first time. Or maybe we'll need entirely new models that treat the sun not as an isolated entity, but as a player in a magnetized galactic ecosystem. One thing's certain, every anomaly is a thread in a larger tapestry, and pulling on it might reveal how intimately connected we are to the invisible forces weaving through the cosmos. The Andromeda Galaxy isn't just our closest galactic neighbor, it's a mirror that reflects our own Milky Way in ways that both comfort and confuse us. At first glance, the two seem like cosmic twins, similar in size, shape, and stellar populations. But peer into their magnetic signatures and the resemblance shatters. Where the Milky Way's magnetic field is a tangled web of chaos, Andromeda's is eerily uniform, as if someone ironed out the wrinkles in its invisible fabric. This stark difference isn't just a curiosity, it's a clue, hinting at how two galaxies following similar blueprints can evolve such contrasting magnetic personalities. One compelling explanation lies in their violent histories. The Milky Way has been a cosmic glutton, devouring dwarf galaxies and absorbing their magnetic imprints like a sponge soaking up ink. Each collision left scars, twisted field lines, turbulent pockets, and regional magnetic anomalies that still ripple through our galaxy today. Andromeda, by contrast, appears to have dined more delicately. Its mergers were fewer, less disruptive, allowing its magnetic field to remain smooth and undisturbed over billions of years. Like a pond after a light rain compared to the Milky Way's storm-tossed ocean, their magnetic differences might simply be a matter of turbulence versus tranquility. But there's another twist lurking in Andromeda's core. At its heart sits a supermassive black hole, just like our own Sagittarius, a star, but this one behaves differently. Observations suggest Andromeda's central black hole is unusually quiet, emitting far less energy than expected. Some scientists speculate this calm demeanor might act like a cosmic thermostat, regulating the galaxy's magnetic field with steady precision. Picture a pot of water simmering gently versus one at a rolling boil. The Milky Way's active core might be churning its magnetic field into chaos, while Andromeda's restraint allows order to prevail. Yet even these explanations don't quite solve the puzzle. Recent radio telescope images reveal faint magnetic tendrils stretching far beyond Andromeda's visible disk, structures with no counterpart in our own galaxy. These ghostly extensions suggest that magnetism might be leaking into intergalactic space, perhaps woven into the cosmic web itself. Could Andromeda be tapping into a larger magnetic network that the Milky Way somehow avoids? Or are we seeing the aftermath of some ancient event, a magnetic echo lingering long after the cause has faded? The implications reach far beyond academic intrigue. If galactic magnetic fields are this sensitive to their history and environment, it means magnetism isn't just a passive feature, it's an active storyteller encoding a galaxy's past in its invisible patterns. By comparing Andromeda's smooth field to the Milky Way's patchwork one, we're not just studying magnetism, we're reading cosmic memoirs, each with its own style, its own scars, its own secrets waiting to be decoded. And that realization changes everything, because if magnetic fields record galactic histories so vividly, then every galaxy we observe becomes a living archive, its invisible ink waiting for us to learn how to read it. Rising from the heart of our galaxy like twin titans, the Fermi bubbles defy everything we thought we knew about cosmic structures. These colossal lobes of scorching gas stretch 25,000 light-years above and below the Milky Way's disk, glowing faintly in gamma rays, a silent testament to some cataclysm that rocked our galactic core. But their most perplexing feature isn't their size or their energy. It's the chaotic web of magnetic fields threading through them, a turbulent scribble that looks nothing like the orderly spirals we see elsewhere in the galaxy. Picture a smoke ring blown by a giant, where instead of dissipating smoothly, the smoke twists into jagged knots and walls midair. That's the Fermi bubble's magnetism fields tangled into impossible shapes, some regions so tightly wound they could snap like overstretched rubber bands. Normally, magnetic fields in space tend to relax into smoother configurations over time, like wrinkles ironed out by cosmic hands. But these fields, they're frozen in frenzy, as if caught mid-explosion. This isn't just random chaos, it's a forensic snapshot of whatever violence created them. The prime suspect, our galaxy's supermassive black hole, Sagittarius, a star. Astronomers have long suspected it wasn't always the quiet neighbor it is today. Millions of years ago, it might have gorged on a colossal meal of gas and stars, belching out jets of energy powerful enough to punch through the galaxy and inflate these bubbles. If true, the twisted magnetic fields could be scars from that eruption, like the crumpled metal left after a bomb blast. But there's a twist. The bubble's edges are razor-sharp, too clean for a purely explosive origin. It's as if something sculpted them with precision, containing the chaos within invisible walls. That's where the alternative theory comes in. Maybe the bubbles weren't forged by the black hole alone, but by a fireworks show of star formation at the galactic center. When massive stars are born in dense clusters, their combined winds and supernova can create shock waves that ripple outward, compressing gas and amplifying magnetic fields in their wake. In this scenario, the bubble's magnetism isn't just debris, it's a cosmic fingerprint, recording the collective fury of billions of stars living and dying in rapid succession. Yet neither explanation fully fits. The bubble's magnetic turbulence is too extreme for a simple stellar wind, but their symmetry doesn't quite match what black hole jets should produce. Some researchers speculate the truth might lie in a hybrid of both a perfect storm where the black hole's eruption coincided with a starburst frenzy, their combined energies twisting magnetism into shapes we're only beginning to decode. Hidden in those magnetic knots could be answers to some of the Milky Way's biggest mysteries. The bubble's fields might explain why certain cosmic rays high-energy particles from deep space seem to rain down on Earth from specific directions. They could reveal how galaxies vent excess energy, preventing their cores from overheating. Most tantalizing of all, they might hold clues about dark matter, as some theories predict its particles could interact with these fields in subtle but detectable ways. One thing's certain, the Fermi bubbles aren't just relics. They're active, evolving structures, their magnetism still crackling with energy from whatever created them. And as we peel back their layers, we're not just studying an anomaly, we're reading the diary of our galaxy's most violent chapter, written in the language of twisted magnetic lines. There's a strange quietude in the cosmos, a silence where we expected chaos. Galaxy clusters, colossal gatherings of hundreds of galaxies bound by gravity, should be seething with magnetic turbulence. Their vast oceans of superheated plasma, stirred by galaxy collisions and black hole jets, ought to churn magnetic fields into frothing whirlpools, yet when we look closely, something's off. In places like the Perseus cluster, the fields are suspiciously smooth, their lines orderly as if ironed flat by some unseen hand. It's as if the universe hit a mute button on the magnetic storm we predicted. Where did all that turbulence go? One possibility lies in the hidden dancers of the cosmos, elusive particles we've yet to detect. Imagine pouring sand into a spinning top. The grains sap its energy, slowing it down. Similarly, hypothetical particles like actions or sterile neutrinos, if they exist, could be bleeding turbulence away, their subtle interactions acting like cosmic friction. Every twist and snap of magnetic field lines might transfer energy into these ghostly particles, quieting the chaos without a trace. It's a tantalizing idea. The missing turbulence could be a whisper pointing us toward new physics, a clue hidden in the hush of galaxy clusters. But there's another, equally compelling explanation. Magnetic fields might dampen themselves on scales we're only beginning to understand. Picture dropping a stone into a pond. The ripples start out jagged and sharp, but over time they smooth into gentle swells. In galaxy clusters, the sheer size of the system could act like that pond, with turbulent energy cascading from small, frantic eddies into vast, languid waves. By the time we observe these fields, the turbulence has dissipated into a near-silent hum. Its energy spread so thin it's virtually undetectable. The implications rattle the foundations of astrophysics. If turbulence can vanish this efficiently, our models of how cosmic magnetism evolves might be missing a crucial piece. We've long assumed turbulent fields persist, shaping gas dynamics and particle acceleration for billions of years. But if they can simply dissolve, it rewrites the rules. Star formation, galaxy evolution, even the distribution of cosmic rays. All could be influenced by this unseen magnetic smoothing. And then there's the wild card. What if the turbulence isn't gone at all? What if it's just shifted into a form we can't yet measure? Some theorists suggest that in the dense plasma of galaxy clusters, turbulent energy might convert into bizarre, large-scale magnetic wave structures so subtle, our current telescopes glimpse only their shadow. Future observatories like the Square Kilometer Array could hunt for these phantom fluctuations, peeling back the veil on this cosmic quiet. The mystery of the missing turbulence isn't just an academic footnote. It's a gaping hole in our understanding of how the universe choreographs its invisible forces. Whether the answer lies in undiscovered particles, self-damping fields, or something even stranger, one thing's clear: the cosmos is still teaching us how to listen. And sometimes what we don't hear speaks the loudest. Fast radio bursts are the universe's most cryptic telegrams, blasts of radio waves so powerful. They outshine entire galaxies for milliseconds before vanishing without a trace. But hidden in their fleeting signals lies a magnetic fingerprint, a clue that could unravel one of astronomy's greatest puzzles. Where do these cosmic flashes come from? When astronomers dissect FRB signals, they often find a telltale twist. The waves arrive polarized, their orientation scrambled as if they've spiraled through a cosmic maze of magnetic fields. The question is, was that twist imprinted at the source, or did it accumulate over billions of light years like snow sticking to a rolling snowball? Take the famous repeater FRB 121102, which fires off bursts like clockwork from a galaxy 3 billion light-years away. Its signals show extreme polarization, suggesting they've battled through a magnetized gauntlet. One leading theory points to Magneta's neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Picture a Magneta's fury. Its crust, strained by unimaginable magnetic forces, could suddenly crack, releasing a shockwave that rips through its own magnetosphere. As the blast plows through this twisted magnetic prison, it might imprint that polarization pattern like a stamp, encoding the star's magnetic rage into the FRB before it even leaves the neighborhood. But there's a twist. Some FRBs show polarization that changes over time, as if the magnetic environment around them is shifting. That's hard to square with a one-time Magneta eruption. Instead, it hints at something more dynamic, perhaps a binary system where a neutron star orbits another dense object, its magnetosphere getting stretched and compressed like taffy with each orbit. Every time the stars swing close, their interacting magnetic fields could trigger a new burst, each one bearing slightly different polarization as the geometry changes. It's like listening to a radio dial being tweaked across cosmic static, with every adjustment revealing a new piece of the magnetic puzzle. Then there's the interstellar journey. Even if an FRB starts pristine, it must traverse the magnetized plasma between galaxies, a soup of charged particles and tangled field lines. While this intergalactic medium is incredibly thin, over billions of light years, its effects add up. The problem, we don't know the exact recipe of that soup. Some regions might be laced with stronger fields, others with weaker. Until we map this cosmic magnetic web, unpicking how much polarization happens en route versus at the source is like trying to guess how much fog dimmed a lighthouse beam without knowing the weather along the coast. The stakes are higher than just solving an astronomical whodunit. If FRBs truly carry imprints of their birth environments, they could become cosmic probes, letting us study magnetic fields in places we'll never visit, like the chaotic outskirts of supermassive black holes or the wreckage of ancient stellar collisions. Already, researchers are using FRBs to measure the universe's missing matter, the diffuse gas too faint to see directly. But if we misread the magnetic contribution, those measurements could be off. It's the astrophysical equivalent of misjudging the wind while navigating by the stars. What's clear is this: FRBs and magnetism are locked in a dance we're only beginning to decipher. Whether the fields they reveal belong to dying stars, crashing galaxies, or the vast voids between them, one thing's certain: each burst is more than a flash in the cosmic dark. It's a message written in the language of magnetic fields, waiting for us to crack the code. And when we do, we might not just find the source of FRBs. We might uncover a new way to see the invisible forces stitching the universe together. Quasars blaze across the cosmos like celestial lighthouses, their brilliance outshining entire galaxies from billions of light years away. But behind that dazzling light show lies a deeper enigma: the invisible magnetic forces that may hold the key to their staggering power. These aren't just any magnetic fields. They're cosmic monsters, strong enough to twist space itself, yet their origins remain shrouded in mystery. Are they born from the chaotic swirl of matter spiraling into the central black hole, or forged in the fiery jets screaming outward at near light speed? The answer could rewrite our understanding of how the universe's most energetic objects operate. Picture the heart of a quasar, a supermassive black hole feasting on an orbiting buffet of gas and dust, the accretion disk glowing white-hot as friction heats it to millions of degrees. In this maelstrom, charged particles spiral along magnetic field lines like cars on a twisted freeway, their motion generating even more magnetism in a self-reinforcing loop. Some theorists argue this process, called the magnetorotational instability, is the engine behind the quasar's magnetic fury. It's like a dynamo on steroids, amplifying weak seed fields into planet-swallowing intensities. But here's the catch: simulations can't quite replicate the extreme field strength we observe. There's a missing piece, something else supercharging this magnetic storm. That's where the jets come in, twin beams of plasma rocketing outward from the quasar's poles, stretching hundreds of thousands of light years into space. These jets aren't just glowing gas, they're magnetized to the core, their particles whipping around helical field lines like beads on a cosmic DNA strand. Some scientists believe the jets don't just carry magnetism, they generate it, acting as particle accelerators that amplify fields through shock waves and turbulence. Imagine blowing up a balloon, then twisting it until the rubber stretches taut. That's what might be happening in these jets, with magnetic energy building until it dominates the system. Yet even this explanation has cracks. Some quasars show bizarre magnetic geometries, their fields tilted or twisted in ways that defy both disk and jet models. Take quasar 3C279, whose polarized light suggests a magnetic helix corkscrewing around its jet, a structure more intricate than any simulation predicts. Then there's the puzzle of relic quasars, dead for billions of years but still glowing faintly in radio waves, their lingering magnetic fields stubbornly persistent. If magnetism comes from active accretion, why hasn't it faded away? The stakes are cosmic. Quasars aren't just distant curiosities, they're time capsules from the early universe, when galaxies were young and black holes grew voraciously. Decoding their magnetism could reveal how these behemoths shaped their surroundings, ionizing gas across vast distances and perhaps even regulating star formation in infant galaxies. Some theories even suggest quasars' magnetic fields could have seeded the larger-scale magnetism we see threading galaxy clusters today, like cosmic lightning, leaving an indelible mark on the universe's canvas. But the real revelation might be about black holes themselves. If we can untangle how quasars generate and sustain their magnetic fields, we might finally understand the fundamental link between gravity and electromagnetism, two forces that seem unrelated, yet here, in the heart of chaos, dance together in perfect, terrifying synchrony. Every flicker of polarized light, every twisted jet, is a clue waiting to be deciphered. And as we piece them together, we're not just solving a quasar's mystery. We're uncovering the hidden rules that govern the most violent, luminous engines in creation. There's something unsettling about a magnetic field with no source, an invisible force lingering in the darkness, untethered to any star, galaxy, or visible structure we can point to. These dark magnetic fields defy our most basic assumptions about how the universe works. We've long known that magnetism arises from moving charged particles, electrons swirling in a star's plasma, ions racing through interstellar gas. But here, in the blackest voids of space, fields persist where no such particles seem to exist. It's as if the cosmos left the lights on in an abandoned house, with no one home to explain why. The first clues came from cosmic rays, high-energy particles streaking across the universe. As these charged particles pass through seemingly empty regions, their paths sometimes bend in ways that suggest an unseen magnetic hand is nudging them. The effect is subtle, like detecting a breeze in a windowless room, but the implications are staggering. If these fields aren't anchored to visible matter, what's holding them up? One haunting possibility is that we're seeing ghosts, magnetic echoes of galaxies long since vanished. Picture a massive galaxy cluster, its magnetic fields woven tight by billions of years of swirling gas. If that cluster were ripped apart by dark energy's expansion, its stars and gas might dissipate into the void, but its magnetism could linger like a cosmic afterimage, fading so slowly it outlasts the structures that birthed it. Yet there's a bolder, even more tantalizing idea lurking in the shadows. What if these fields aren't relics at all, but signs of something far stranger? Dark matter makes up 85% of the universe's mass, yet it famously refuses to interact with light or ordinary matter except through gravity. But what if it interacts with itself through some hidden electromagnetic force? Most models assume dark matter is magnetically neutral, but nature has a habit of upending our assumptions. If even a fraction of dark matter particles carried a faint charge, their collective motion could generate these ghostly fields, weaving an invisible magnetic web through the cosmos. The evidence is still circumstantial, but the pieces are falling into place. In certain galaxy clusters, the distribution of dark matter aligns suspiciously with unexplained magnetic structures, as if the two are dancing to the same tune. Meanwhile, simulations of the early universe show that if dark matter had even a trace of electromagnetic interaction, it could have seeded magnetic fields strong enough to persist to the present-day fields that would now hang in space like forgotten cobwebs, untouched by the luminous matter around them. Of course, not all scientists are convinced. Skeptics argue that these dark fields might simply be tied to ultra-faint matter we haven't detected yet, whispers of gas too diffuse to see, or the faint glow of primordial hydrogen lurking just beyond our telescope's reach. But that's the thrill of this mystery. Whether these fields are echoes of the dead, signatures of the invisible, or something even more unexpected, they're forcing us to rethink one of physics' most basic questions. What does it take to create a magnetic field in the first place? Every new observation chips away at our assumptions, reminding us that the universe is always more inventive than we imagine. And somewhere in these dark, magnetized voids, the cosmos might be hiding its most revolutionary secret yet, a fundamental force operating in plain sight, yet just beyond our grasp. The Milky Way doesn't drift through space alone. It's wrapped in an invisible magnetic embrace, a vast halo stretching hundreds of thousands of light years into the void. But this cosmic shield is anything but uniform. Like a lopsided cocoon, it's thicker and stronger in some directions, almost threadbare in others. This unevenness isn't just a curiosity, it's a cosmic crime scene, and the clues point to a history of galactic violence and upheaval. One prime suspect, the Milky Way's messy eating habits. Over billions of years, our galaxy has devoured smaller dwarf galaxies, their stellar remains smearing across the halo like fingerprints. Each collision could have left magnetic scars as the turbulent merger of gas and stars twisted existing field lines into knots. Picture a spoon stirring honey into tea. The swirls linger long after the motion stops. Similarly, the Sagittarius dwarf galaxy, currently being torn apart by the Milky Way's gravity, might be seeding new magnetic turbulence into the halo's southern regions, explaining why the field there appears unusually tangled. Yet mergers alone can't account for the halo's full asymmetry. Look toward the galactic center, and the magnetic field grows stronger, as if something is pumping energy outward. Here, the culprit might be the supermassive black hole, Sagittarius, a star. Though quiet now, it's likely had violent outbursts in the past, eruptions that blasted magnetized plasma into the halo like cosmic geysers. These outflows could have sculpted the field's unevenness, leaving behind magnetic bubbles that persist like fossils. Meanwhile, the relentless solar winds from countless stars, especially in the galaxy's crowded core, might reinforce this pattern, their collective pressure shaping the halo's invisible contours. But the halo isn't just a relic, it's a frontline defender. Intergalactic space is flooded with cosmic rays, high-energy particles racing toward the Milky Way at nearly light speed. Without the halo's magnetic web, these projectiles would bombard the galactic disk unchecked, potentially sterilizing fledgling planets or disrupting star formation. Instead, the field acts like a celestial sieve, deflecting some particles while channeling others toward the poles, where they spark auroras in the atmospheres of distant worlds. This protective role makes the halo's asymmetry more than academic. It could determine which corners of the galaxy are hospitable to life. The mystery deepens when we compare our halo to others. Andromeda's magnetic shield, for instance, is far more symmetrical, suggesting its history has been less tumultuous. Is the Milky Way's lopsidedness a fluke or a common outcome for galaxies that feast as greedily as ours? The answer might lie in upcoming radio telescope arrays, which could map the halo's finer structure by tracing how its fields bend the light of distant quasars. Every distortion in that light is a clue, a piece of the puzzle waiting to snap into place. What's clear is this: our magnetic halo isn't just a passive bystander. It's a dynamic, evolving structure, shaped by the galaxy's past and actively shaping its future. And somewhere in its uneven embrace, hidden in the ebb and flow of invisible forces, lies the untold story of how the Milky Way became the galaxy we call home. Stars don't just shine, they seethe with hidden turmoil, their magnetic fields twisting and flipping in ways that make our sun's predictable cycles look tame by comparison. Imagine a star 10 times the sun's mass, its magnetic poles reversing not every 11 years, but chaotically sometimes flipping twice in a century, other times locking into place for millennia. Then there are the real oddballs like Tau Boötis, a star caught red-handed with not 2 but 3 magnetic poles, its field lines knotted into a celestial pretzel. This isn't just stellar unpredictability, it's a cosmic rebellion against the neat patterns we thought governed magnetism. The roots of this chaos might lie deep within a star's churning heart. Unlike the Sun, which rotates relatively sedately, massive stars often spin at breakneck speeds, their equatorial regions whipping around in days instead of weeks. This rapid rotation could tangle internal plasma flows into a frenzied dynamo, amplifying and destabilizing magnetic fields like an overclocked engine. Picture a pot of boiling water, stir it gently, and the currents stay orderly. Crank up the heat and turbulence erupts. For stars, that turbulence might scramble their magnetic poles into temporary chaos before gravity and rotation eventually restore order, or not. But rotation alone doesn't explain the full spectrum of stellar magnetic mischief. Take binary systems where 2 stars orbit each other in a gravitational dance. In cases like HD 98088, tidal forces from a close companion might stretch and warp one star's magnetic field, forcing it into bizarre configurations. It's like holding a magnet near a compass. The needle doesn't just point north anymore. Similarly, planets could play puppeteer. A gas giant orbiting unusually close to its star, like a hot Jupiter, might plow through the stellar magnetosphere, disrupting field lines like a ship churning wake through water. Then there's the wild card, fossil fields. Some stars might inherit their magnetism from the dense molecular clouds they were born in, preserving primordial magnetic imprints like cosmic heirlooms. These ancient fields could resist the dynamo's smoothing effects, leading to strange, frozen-in patterns that defy contemporary physics. The star Sigma Orionis E, for instance, sports a magnetic equator tilted sharply against its spin axis, a configuration that looks more like a relic than something actively generated today. Why does this matter beyond celestial curiosity? Because stellar magnetism isn't just a local phenomenon, it shapes the very space around these stars. Erratic flips could bombard orbiting planets with lethal radiation surges, sterilizing potential life or stripping atmospheres entirely. Double or triple magnetic poles might create dead zones where charged particles get trapped, shielding some worlds while exposing others. And for humanity's future, if we ever hope to navigate or settle near other stars, decoding their magnetic moods will be as crucial as checking the weather forecast before sailing. The deeper we look, the clearer it becomes. Magnetic diversity in stars isn't a bug, it's a feature. Each anomaly is a clue, a piece of a puzzle that stretches from the birth of stellar systems to the fates of the planets they host. And as we piece together why some stars flip like clockwork while others spiral into magnetic anarchy, we're not just studying distant suns, we're uncovering the invisible forces that might one day dictate our survival among them. Galaxy clusters are cosmic cities, vast metropolises where hundreds of galaxies huddle together, bound by gravity's unrelenting grip. But between these islands of stars lies something far stranger, a seething ocean of million-degree gas, so hot it glows in X-rays. And threading through that inferno are magnetic fields, invisible yet powerful, their patterns as intricate as spider silk stretched across the void. These aren't random scribbles, they're cosmic archives, their twists and turns encoding the cluster's most violent chapters. Take the Coma cluster, a bustling galactic hub 300 million light-years away. When astronomers mapped its magnetic fields, they expected chaos. After all, this cluster is a demolition derby of colliding galaxies. Instead, they found eerie coherence. The fields spiral outward from the cluster's core like the arms of a pinwheel, as if sculpted by some unseen cosmic hand. One theory points to the cluster's central galaxy, a behemoth called NGC 4874, whose supermassive black hole might be pumping ordered magnetic energy into the surrounding gas like a colossal dynamo. But here's the twist: these spiral patterns stretch far beyond where any single galaxy's influence should reach. It's as if the entire cluster remembers some ancient spin, a primordial rotation frozen into magnetism when the universe was young. Then there's the Bullet cluster, a cosmic crime scene where two galaxy clusters collided head-on. The smash-up was so violent, it stripped the gas from the galaxies, leaving it trailing behind like cosmic exhaust. Yet when researchers examined this wreckage, they found magnetic fields not just in the gas, but in the seemingly empty regions between fields aligned in sharp, radial lines like spokes on a wheel. These patterns suggest something extraordinary. That cluster mergers don't just scramble magnetism, they can amplify and organize it, turning chaos into order through sheer brute force. Imagine two hurricanes colliding and emerging with their winds perfectly synchronized. That's the level of paradox we're dealing with, but not all clusters play by these rules. Some, like the Perseus cluster, show magnetic fields tangled into knots, their lines crisscrossing like a bowl of spaghetti. The difference might come down to age. Younger, still-forming clusters could be like turbulent teenagers, their magnetism a mess of growing pains. Older, relaxed clusters might have smoothed their fields over billions of years, like wrinkles fading from a well-worn face. Yet even this explanation has holes. Why do some mature clusters retain patchy, disordered fields while others become models of magnetic elegance? The answer might lie in the galaxies themselves. As galaxies orbit through the cluster, their motion could drag magnetic field lines like ships churning wakes in water. Over time, these individual stirs might combine into larger currents, shaping the cluster's overall magnetic personality. Some simulations suggest that particularly massive galaxies, or those on plunging orbits near the core, could dominate this process like conductors guiding a cosmic magnetic orchestra. What's truly astonishing is how long these patterns endure. Galaxy clusters are among the oldest structures in the universe, and their magnetic fields might be just as ancient. That means the spirals and spokes we see today could be fossils, preserving the violence of collisions that happened before Earth even formed. They're not just shaping the cluster's present, they're whispering secrets about its past. And that's what makes this uncharted territory so thrilling. Every twisted field line, every unexpected alignment, is a piece of a puzzle that spans billions of years. By decoding these magnetic maps, we're not just studying galaxy clusters, we're reading the autobiography of the cosmos itself, written in the language of invisible forces. Ultra-diffuse galaxies shouldn't exist, at least, not by the rules we thought governed cosmic magnetism. These ghostly giants stretch as wide as the Milky Way, yet their starlight is so faint, they nearly vanish against the black velvet of space. With so few stars and so little visible matter, Their magnetic fields should be whispers, barely detectable. But the universe loves a paradox. Many UDGs hum with magnetism as strong as far denser galaxies, their invisible force lines crisply organized like cosmic street grids in near-empty towns. This isn't just puzzling, it's a direct challenge to our understanding of how magnetism seeds and survives across cosmic time. One compelling theory paints UDGs as cosmic phantoms, galaxies that once brimmed with promise before something went terribly wrong. Picture a young galaxy, rich with gas and crackling with star formation, its magnetic field amplified by the churn of newborn stars and supernova. Then, perhaps through a brutal encounter with a larger galaxy, its gas gets stripped away, star formation grinds to a halt, and the galaxy becomes a shadow of itself. But the magnetism that lingers, frozen in time like a fly in amber. The galaxy fades, but its magnetic memory remains, a relic of its former glory. Observations of UDGs near massive galaxy clusters support this idea. Their distorted shapes hint at past gravitational assaults that might have robbed them of their star-forming potential while leaving their magnetic skeletons intact. Yet there's a twist. Some UDGs live in isolation, far from the gravitational bullies of galaxy clusters. These cosmic hermits couldn't have been stripped by violent encounters, yet they, too, boast surprisingly strong magnetic fields. This raises a tantalizing alternative. What if UDGs aren't failed galaxies at all, but ones that never ignited properly to begin with? In this scenario, their magnetism might stem from an unusual birth. Imagine a vast cloud of primordial gas, laced with weak magnetic fields from the early universe, collapsing into a galaxy, but so inefficiently that stars only sputter to life in scattered patches. The fields, stretched and amplified by the galaxy's slow rotation, could have organized into coherent patterns without the usual stellar fireworks, creating a magnetic galaxy that never quite lit up. The plot thickens when we examine UDGs with extreme properties like Dragonfly 44, a galaxy with the mass of the Milky Way but only 1% of its stars. Its dark matter halo is colossal, suggesting it holds secrets about how magnetism interacts with the invisible scaffolding of the cosmos. Could dark matter's gravitational pull be shaping these fields in ways we don't yet grasp? Or are we seeing hints of an entirely new magnetic process, one that operates in near darkness, independent of the stars we're used to studying? Then there's the wild card, turbulence. Even sparse galaxies have gas, and where there's motion in ionized gas, there's potential for magnetism. Some UDGs show faint, swirling gas clouds that might be stirred by unseen forces, perhaps leftover turbulence from ancient supernova or the gentle push of cosmic rays. Over billions of years, this subtle motion could sustain weak magnetic fields, like a breeze keeping a windmill turning long after the storm has passed. What makes UDGs so electrifying isn't just their defiance of expectations, it's what they reveal about magnetism's tenacity. These galaxies challenge the notion that strong magnetic fields require bustling stellar factories. Instead, they suggest magnetism can persist, even thrive, in the quietest corners of the universe, woven into the fabric of galaxies regardless of their visible brilliance. Every faint glow from a UDG is a reminder. The cosmos writes its rules in invisible ink, and we're only beginning to trace the letters. Cosmic dust might seem insignificant, tiny specks adrift in the void between stars, but these microscopic grains hold a magnetic secret that's rewriting how we see the universe. Picture a trillion minuscule compass needles, each aligning with the invisible pull of cosmic magnetism, subtly twisting the light that passes through them. This phenomenon, called starlight polarization, lets astronomers trace magnetic fields across galaxies, turning dust into an unlikely cartographer of the unseen. Yet the deeper mystery isn't just what these grains reveal, it's how they respond to magnetism at all. How does something smaller than a wavelength of light sense the universe's hidden forces? The answer might lie in the dust itself, and its story is stranger than fiction. Take a single grain of interstellar dust, perhaps a fleck of silicate or carbon, no wider than a virus. In the harsh environment of space, bombarded by radiation and plasma, these grains aren't inert. Many become electrically charged, losing or gaining electrons until they're like microscopic magnets, their behavior dictated by the surrounding fields. But here's the twist. Some dust might be inherently magnetic, containing tiny inclusions of iron or other ferromagnetic materials. Imagine a grain of sand with a core of magnetite, like a cosmic iron filing, snapping into alignment with galactic fields as effortlessly as a compass needle finding north. These particles wouldn't just respond to magnetism, they'd remember it, locking in the direction of ancient fields like fossils frozen in time. Yet alignment isn't always straightforward. In denser regions like the swirling arms of a galaxy, dust grains don't just passively align, they pirouette, spun by collisions with gas molecules and buffeted by turbulence. This dance creates a paradox. The very fields the grains reveal are also constantly jostling them out of position. To complicate things further, some grains might spin so fast they ignore the magnetic field entirely, like a top resisting a gentle nudge. Others could be trapped in magnetic dead zones, where local forces cancel out the larger galactic field. It's as if the universe encoded its magnetic secrets in a cipher, and dust grains are both the key and the lock. The implications stretch far beyond mapping fields. Dust polarization might hold clues to one of astronomy's oldest questions: how do stars form? In stellar nurseries, magnetic fields channel collapsing gas into swirling disks, guiding the birth of new suns. Dust grains caught in this gravitational whirlpool could reveal the hidden scaffolding that shapes planetary systems. Some theories even suggest that aligned dust grains might help molecules like hydrogen form on their surfaces, seeding the chemistry of life before planets exist. But the real revolution lies in what we haven't seen yet. Certain wavelengths of polarized light hint at dust behaviors that defy current models, perhaps due to exotic grain shapes like needle-like filaments or flat platelets that align in unpredictable ways. Or maybe the dust is telling us the fields themselves are stranger than we thought, with tiny scale fluctuations invisible to our telescopes. Every flicker of polarized starlight is a whisper from the dark, urging us to look closer, think differently. So while cosmic dust may seem like the universe's afterthought, it's actually one of its most eloquent storytellers. These minuscule particles don't just drift, they communicate, translating the language of invisible forces into something we can finally begin to understand. And as we decode their magnetic secrets, we're not just mapping the cosmos, we're learning to read its hidden rhythms one grain at a time. White dwarfs should be the quiet retirees of the stellar world, dense, cooling embers of stars that have burned through their fuel. But some of these cosmic pensioners are anything but peaceful. Imagine an Earth-sized cinder with a magnetic grip so fierce, it could rip atoms apart from thousands of miles away. These aren't rare outliers. Nearly 10% of white dwarfs boast fields thousands to millions of times stronger than Earth's, while others show no trace of magnetism at all. This split personality isn't just random, it's a cosmic whodunit, and the clues point to dramatic origins. Take WD-818-049, a white dwarf with a magnetic field so intense it's twisted light into knots. Spectroscopic observations reveal its field isn't a simple dipole like Earth's, but a chaotic tangle, as if someone took a bar magnet and wrung it like a dish rag. One compelling explanation: this star didn't die alone. Simulations suggest that when two white dwarfs spiral together in a gravitational dance, their merger can churn plasma into a frenzied dynamo, amplifying magnetic fields to staggering levels. It's like blending two cups of coffee, except here, the swirling motion doesn't just mix, it electrifies, leaving behind a magnetic monster where there was none before. But mergers can't explain every magnetized white dwarf. Some, like Sirius B, the faint companion to our sky's brightest star, show surprisingly weak fields despite their violent pasts. This hints at another possibility: fossil fields. During their red giant phase, stars shed their outer layers, but their cores might retain traces of ancient magnetism, like a ship's logbook preserving records of long-ended storms. If the original star had a strong magnetic field, the collapsing core could concentrate that energy, squeezing it into a dense magnetic relic. Then there's the planetary fallout. A white dwarf's magnetism isn't just a curiosity, it's a potential death sentence for any surviving worlds. Planets orbiting these stars face relentless magnetic hurricanes, their atmospheres stripped atom by atom and ionized into glowing auroras. Worse, the field can warp the very debris disks of shattered planets, funneling metallic vapor into strange, uneven rings. In extreme cases, like the white dwarf GD356, the magnetic field acts like a cosmic shredder, twisting planetary material into magnetized filaments that glow like ghostly cobwebs under X-ray telescopes. Yet the most tantalizing clue lies in the exceptions, the white dwarfs that defy categorization. A handful, like WD 1953-011, cycle between magnetic and non-magnetic states over decades, as if flicking a cosmic switch. Others show patchy fields, with magnetic hotspots scattered across their surfaces like islands in a non-magnetic sea. These oddballs suggest magnetism in white dwarfs isn't just about origin stories. It's about evolution, decay, and perhaps even reawakening. What's clear is this: white dwarfs are far more than inert stellar corpses. They're dynamic laboratories where magnetism can emerge, fade, or flare back to life under conditions we're only beginning to understand. And every magnetic field we detect or fail to detect is a piece of a puzzle that stretches from the deaths of stars to the fates of the worlds they leave behind. The universe's first magnetic whispers might still be echoing across the cosmos, hidden in the afterglow of creation itself. Imagine the Big Bang's searing plasma, 1 trillion degrees hot, swirling with charged particles that could have woven magnetic fields into the fabric of spacetime. If those primordial fields survived, their faint signatures could be etched into the cosmic microwave background, the oldest light in existence. It's like searching for fossilized ripples from the universe's first breath. Scientists hunt for these magnetic ghosts by studying the CMB's polarization, the subtle directional twist in its light. A primordial field would have sculpted this polarization in telltale patterns, like invisible fingers dragging through wet paint. Some models predict swirling B-mode patterns, distinct from the curls caused by gravitational waves. Others suggest more elusive distortions, as if the CMB's light passed through a cosmic prism of ancient magnetism. But after decades of scrutiny, from ground-based telescopes like BICEP to space missions like Planck, no definitive signal has emerged. The universe, it seems, is holding its cards close. Why does this absence tantalize researchers? Because if primordial magnetism existed, it would demand entirely new physics. The standard model can't explain how large-scale fields could arise so early. They'd need exotic processes like phase transitions in the newborn universe or interactions with hypothetical particles we've yet to discover. A detection wouldn't just reveal magnetism's origins. It could expose cracks in our foundational theories, hinting at dimensions or forces beyond our current understanding. Yet the search isn't just about what we haven't found. The very absence of a signal speaks volumes. It rules out entire classes of theories about the universe's infancy, narrowing the possibilities for how matter, energy, and forces behaved in those first unimaginable moments. Some researchers now speculate that if primordial fields exist, they might be too weak for current telescopes or hidden in higher-order patterns we're only beginning to model. Others propose radical alternatives. Perhaps the fields decayed over time or were erased by some cataclysm we've yet to imagine. The quest continues with next-generation observatories like the Simons Array and CMB-S4, designed to probe deeper into the CMB's secrets. They're not just looking for magnetism, they're chasing the shadow of the universe's first dynamo, a machine that might have run on laws of physics we've yet to write. And if they find it, that whisper from the dawn of time could rewrite our cosmic story, revealing that magnetism isn't just a feature of the universe, it's one of its original architects. Galactic collisions are cosmic ballets of destruction and creation, spiraling arms torn asunder, stars flung into the void, and vast clouds of gas set ablaze with newborn suns. But beneath this visible chaos, another drama unfolds in the shadows, the clash of invisible magnetic empires. When two galaxies collide, their fields don't simply add together like ingredients in a soup. They tangle, snap, and reorganize in ways that could decide whether the merged galaxy becomes a stellar nursery or a silent graveyard of dead stars. Consider the antennae galaxies, two spirals locked in a slow-motion wreck. Radio telescopes reveal their magnetic fields stretched into bizarre bridges between them, as if the galaxies are stitching themselves together with invisible thread. In some regions, the fields amplify, turbocharging star formation by compressing gas into dense knots. Elsewhere, they cancel out, leaving dead zones where star birth grinds to a halt. It's a cosmic tug of war where magnetism acts as both architect and saboteur of galactic rebirth. Why such unpredictability? Magnetism in colliding galaxies isn't just about the strength of the original fields, it's about geometry. Picture two bar magnets thrown into a washing machine. Depending on how they collide, they might snap together, repel violently, or spin into unstable arrangements. Galaxies do the same, but on scales so vast, the outcomes ripple across millions of years. If their fields align just right, they can funnel gas into furious starbursts, like the legendary blueberries in the tadpole galaxy's tail. Misalign them, and the energy dissipates into turbulence, leaving behind a gas-starved elliptical galaxy, a cosmic burnout. Simulations struggle to capture this complexity. Supercomputers can model gravity's role in collisions with stunning accuracy, but magnetism adds a layer of chaos. Tiny fluctuations in initial conditions, say, the tilt of one galaxy's magnetic axis, can snowball into wildly different outcomes. Some models suggest mergers might even spawn large-scale, magnetic reconnection events, where fields break and realign, unleashing bursts of energy capable of reheating gas across entire galactic volumes. Yet the most tantalizing clues come from outliers. Take NGC 1275, a post-merger galaxy with a magnetic field that coils like a double helix around its core. Nothing in simulations predicted this structure. Then there's ARP 220, the Atoms for Peace galaxy, where magnetism seems to have orchestrated a lopsided starburst, igniting stars on one side while leaving the other eerily dark. These oddballs hint at forces we're only beginning to grasp, perhaps interactions with hidden dark matter halos, or relics of pre-collision magnetic turbulence frozen into the merger's DNA. What's at stake isn't just academic. If magnetism steers galactic collisions, it could explain why some galaxies in the early universe formed stars at breakneck speeds while others stalled. It might even hold the key to why modern galaxies like the Milky Way are so magnetically quiet compared to their ancient counterparts. Every galactic wreck we study is a time capsule, preserving the moment when invisible forces wrote their signature across the cosmos. And as we decode that signature, we're not just reconstructing collisions, we're uncovering the hidden rules that govern how galaxies live, die, and rise again from the chaos. Deep in the swirling oceans of cosmic plasma, where charged particles dance to the tune of invisible forces, there's a phenomenon so peculiar it defies intuition: magnetic islands. These aren't landmasses floating in space, but self-contained loops of magnetic field lines, pinched off from their surroundings like bubbles rising in a boiling pot. Picture a river suddenly curling back on itself, forming a whirling eddy that traps everything inside. That's what happens in these plasmas. Energy and particles get snared in these isolated pockets, creating temporary cosmic prisons where the usual rules of magnetic flow no longer apply. The birth of these islands is where the mystery deepens. One camp of physicists argues they're forged in the fires of magnetic reconnection, the same explosive process that powers solar flares. When field lines snap and reconnect, they might not just release energy, they could also spit out these self-contained loops like sparks scattering from a frayed wire. Simulations show how, in the chaos of reconnection, magnetic fields can twist into helical shapes, sealing off sections of plasma into these island structures. It's as if the universe has a secret knack for tying magnetic knots when we're not looking. But there's a rival theory that's just as compelling. Some researchers believe these islands emerge from plasma instabilities, natural wobbles in the turbulent sea of charged particles. Imagine blowing across the surface of a cup of coffee. The ripples you create can sometimes merge into larger swirls. In plasma, tiny fluctuations in density or current can amplify, warping magnetic fields until they fracture into these self-contained islands. This wouldn't require the violent snap of reconnection, just the right conditions for plasma to fold in on itself, like a baker kneading dough until pockets of air form inside. The stakes of this debate stretch far beyond academic curiosity. Here on Earth, scientists battling to harness fusion energy, the process that powers the sun, run into magnetic islands all the time in their experimental reactors like tokamaks. These structures can wreak havoc, trapping heat and disrupting the delicate balance needed to sustain a fusion reaction. If we could predict how and why islands form, we might finally tame them, unlocking the dream of clean, limitless energy. It's like trying to control a wildfire. If we understand where the sparks fly, we can stop them from burning down the house. Yet the cosmos keeps throwing us curveballs. Recent observations of the solar wind, the stream of charged particles constantly blowing from the sun, reveal magnetic islands far larger and more stable than anyone predicted. Some persist for hours, even days, drifting through space like invisible jellyfish. How do these structures survive without dissipating? Are they being constantly fed energy? Or is there some hidden mechanism that lets them resist the universe's natural tendency toward chaos? Every new discovery peels back another layer of this enigma. Whether born from the violence of reconnection or the subtle dance of instabilities, magnetic islands are a reminder that even in the most extreme environments, the universe has a habit of creating order within disorder. And somewhere in their twisted loops lies a secret, not just about the cosmos, but about how we might one day bend its most elusive forces to our will. Brown dwarfs are cosmic misfits, too massive to be planets, yet too puny to light the nuclear fires that make a true star. These dim, failed suns should be quiet, uneventful places. But the universe loves defying expectations. Many brown dwarfs crackle with magnetic fields strong enough to shame Jupiter, sparking dazzling auroras that dance in their frigid atmospheres without the heat of fusion to power them. It's like finding a flashlight that glows brilliantly without batteries, a phenomenon that shouldn't work yet does spectacularly. The puzzle starts with their sluggish spin. Stars like our Sun generate magnetism through churning, electrified gas, their rapid rotation stirring up a dynamo in their cores. Brown dwarfs, though, often rotate as slowly as old grandfather clocks, their interiors too cool and thick for the usual stellar dynamo to take hold. So where does their magnetic punch come from? One radical theory suggests their magnetism might be rooted in deeper, stranger physics. Picture a brown dwarf's interior, a dense soup of degenerate matter where electrons move freely like a metallic fluid. Under extreme pressure, this quantum soup could sustain electric currents for billions of years, generating fields through a process more akin to a planet's core than a star's furnace. Then there's the wild card, convection. Unlike stars, where heat blasts outward from a nuclear core, brown dwarfs rely on residual warmth from their formation, slowly leaking through layers of churning atmosphere. Some models suggest this sluggish circulation might amplify weak magnetic seeds through a feedback loop, like a lazy river gaining unexpected turbulence where currents collide. Observations of variable radio emissions from brown dwarfs like LSRJ 1835 support this idea, their flickering signals hinting at magnetic hotspots where convection cells breach the surface. But the real enigma lies in their auroras. On Earth, these shimmering lights are driven by solar wind particles spiraling along our planet's magnetic field lines. Brown dwarfs have no nearby star to bombard them with such particles, yet their auroras blaze on. One possibility, their own moons might be the culprits. Just as Jupiter's volcanic moon Io seeds its auroras with charged particles, a brown dwarf's satellites could be sputtering ionized material into its magnetic grip. Alternatively, the dwarfs might be self-sufficient, their feeble atmospheres leaking enough ions to fuel the light show from within. The stakes of this mystery reach far beyond brown dwarfs themselves. If these objects generate magnetism through entirely novel mechanisms, it could blur the line between stars and planets, forcing us to rethink how magnetic fields arise across the cosmic spectrum. Imagine a world where gas giants like Jupiter, given enough time and mass, evolve magnetic personalities more like failed stars than planets. Or consider the implications for exoplanets. Could cold, brown dwarfs host habitable moons, their auroras providing both light and radiation shielding in lieu of a nurturing sun? Every flicker of radio static, every anomalous aurora from these cosmic in-betweeners is a clue waiting to be deciphered. They're proof that magnetism, that most familiar of forces, still has tricks up its sleeve hidden in the cold, dark places where the universe refuses to play by the rules we've written. And that's what makes this uncharted territory so thrilling, because in the quiet gloom of a brown dwarf's atmosphere, we might just find the key to rewriting the magnetic playbook for everything, from the smallest rogue planet to the brightest star. Galactic winds are the universe's great exhale rivers of gas streaming from galaxies at millions of miles per hour, carrying with them not just matter, but something far more elusive, magnetic energy. Picture a storm rolling off the ocean, but instead of rain, it flings invisible force lines into the void. These winds, powered by the fury of star formation or the violence of supermassive black holes, don't just shape their home galaxies, they might be the unseen architects of magnetism across the cosmos. Yet for all their grandeur, their journey remains one of astronomy's most tantalizing mysteries. What happens to these fields as they race into the intergalactic wilderness? Do they fade into oblivion, or do they persist, weaving magnetism into the fabric of deep space? Take starburst galaxies like M82, where stars are born in such frenzied bursts. Their collective energy drives winds fierce enough to strip smaller galaxies bare. Radio telescopes reveal these outflows are magnetized, their fields twisted into colossal helices by the galaxy's rotation. But here's the puzzle. As the wind travels hundreds of thousands of light years from its source, the magnetism doesn't just vanish. Instead, it lingers, imprinting itself on the surrounding gas like a cosmic tattoo. Some theories suggest these fields could act like scaffolding, guiding the wind's expansion and even shaping the next generation of galaxies that might form in its wake. Then there's the role of black hole-driven winds like those roaring from quasars. These jets, hotter and faster than their starburst counterparts, are threaded with magnetic fields so intense they accelerate particles to near light speed. Simulations show that when these magnetized winds collide with the tenuous gas between galaxies, they don't just dissipate. They trigger shockwaves that amplify and stretch the fields, potentially turning a localized outburst into a far-reaching magnetic web. It's as if the universe has a hidden recycling program where galaxies expel their magnetic energy only for it to be reforged in the crucible of intergalactic space. But not all winds are created equal. Some galaxies, like those in quiet clusters, emit gentler outflows where magnetism might fade before it travels far. Others, like merging galaxies, produce chaotic gusts where fields tangle and cancel out. This variability raises a profound question. Is there a threshold, a critical energy or density, that determines whether a galactic wind's magnetism survives its journey? If so, it could explain why some regions of the cosmos hum with magnetic energy while others remain eerily silent. The stakes of this mystery stretch beyond theory. If galactic winds are indeed seeding the voids with magnetism, they could be solving one of astrophysics' oldest riddles. How did the universe, born without magnetic fields, become so thoroughly magnetized? Every wind, every outflow might be a cosmic painter's brushstroke, adding invisible color to the darkness, and that realization changes everything. Because if magnetism isn't just a local phenomenon but a galactic export, then the emptiness between galaxies isn't empty at all. It's a living network, charged with the breath of countless stars and black holes, whispering secrets we're only beginning to hear. We stand on the brink of a magnetic revolution in astronomy, one that will peel back the cosmic veil like never before. The Square Kilometer Array, a sprawling network of radio antennas now rising across continents, isn't just another telescope. It's a time machine tuned to the universe's hidden frequencies, capable of detecting magnetic whispers from the dawn of galaxies. When fully operational, its sensitivity will let us trace fields so faint they've been invisible until now, like finally seeing the invisible ink scrawled between the lines of cosmic history. Consider what this means for the great puzzles we've explored. The SKA could settle the debate over primordial magnetism by hunting for its fingerprints in the cosmic microwave background with precision we've never dreamed of. It might catch magnetic monopoles in the act if they exist, by spotting the distinct radiation patterns they'd leave while zipping through interstellar space. Even more tantalizing, it could map the magnetic web connecting galaxies with such clarity. We'd see whether these fields guide cosmic evolution or merely follow it. But the surprises won't stop at large-scale structures. Quantum mechanics and cosmic magnetism have always lived in separate realms, one governing the impossibly small, the other stretching across light years. Yet the SKA's successor instruments, like ultra-sensitive quantum sensors, might bridge this divide. Imagine detecting how virtual particles, fleeting quantum fluctuations in empty space, interact with galactic magnetic fields. Such observations could reveal if spacetime itself has a subtle magnetic texture, a possibility that would rewrite physics from the ground up. Then there's the wild card, dynamos we can't yet conceive. Just as the first radio telescopes uncovered quasars and pulsars objects, no one predicted the next generation could expose entirely new magnetic phenomena. Perhaps galaxies harboring anti-dynamos that suppress fields instead of amplifying them, or rogue planets with magnetic tails stretching halfway to their stars. The universe has consistently shown us that wherever we draw boundaries, it finds a way to cross them. What makes this moment so electrifying isn't just the technology, it's the sheer scale of our ignorance. For every magnetic mystery we've outlined, there are dozens we haven't even imagined yet. The SKA and its peers won't just provide answers, they'll redefine the questions, exposing gaps in our understanding we didn't know existed. And that's the true promise of cosmic magnetism research. Not just mapping the unknown, but discovering new categories of the unknown waiting to be explored. One thing's certain, the textbooks of 2030 won't just have new chapters, they'll need entirely new frameworks to contain what we're about to learn. From the quantum foam to the cosmic web, magnetism is the thread tying it all together, and we're finally pulling at its ends. Where it leads, no one can say, but the journey will transform how we see the universe and our place within it. From the birth of galaxies to the echoes of the Big Bang, cosmic magnetism is a force shaping the universe in ways we're only beginning to grasp. These 32 uncharted territories represent the frontier of our understanding, each a puzzle waiting to be solved. Think of them as cosmic breadcrumbs scattered across the void, each one leading us deeper into the mystery of how invisible forces stitch the fabric of reality together. Whether it's the ghostly fields lurking in galactic voids or the explosive snap of magnetic reconnection near black holes, every discovery peels back another layer of the universe's hidden blueprint. What makes this journey so thrilling isn't just the scale of these mysteries, it's how they force us to rethink the rules we thought were set in stone. Take something as fundamental as magnetism itself. For centuries, we've assumed it arises solely from moving charges, yet the cosmos keeps showing us fields where no obvious source exists. Could dark matter be whispering to us through these anomalies? Or are we glimpsing remnants of physics from the universe's first moments, preserved like fossils in the magnetic lattice of space? The answers won't just fill textbooks, they could redefine our place in the cosmos. And the tools we're building to chase these answers are just as revolutionary as the questions themselves. The Square Kilometer Array, with its continent-spanning sensitivity, will map magnetism in ways akin to how the Hubble telescope unveiled the visual universe. Quantum sensors dangling from satellites might detect fluctuations in spacetime's very fabric, revealing whether magnetism is woven into dimensions we can't yet perceive. Even artificial intelligence is joining the hunt, sifting through petabytes of data to spot patterns no human eye could catch. This isn't just progress, it's a paradigm shift where every observation could rewrite what we know. Yet for all our technology, the most humbling realization is how much remains unseen. The universe has spent billions of years encoding its secrets in magnetic fields, and we've barely begun to decipher them. Perhaps the greatest lesson isn't in the answers we've found, but in the questions we've yet to ask. Because somewhere out there, beyond the edge of our current understanding, the cosmos is still writing its story, one magnetic ripple at a time. So what's next? That's the beauty of exploration. The next breakthrough might come from a lone researcher staring at a data anomaly, or a telescope catching a flicker of polarized light from halfway across the universe. One thing's certain, the journey is far from over, and every discovery brings us closer to answering humanity's oldest questions. What will we find next? The universe is waiting to show us. Don't forget to like, subscribe, and share your thoughts in the comments below. Let's explore the